floor is
Thank you.
yours.
Appreciate very much the invitation. I always like to come back to Croatia. I started coming here since 1993. And I think I'm still on the guest faculty in FER, right? So I should be able to revamp this after I finished my administrative duties in the US. And I'm back into research, which I like very much. So my talk today is going to deviate from strictly underwater vehicles, even though when I was in Louisiana, my group was involved in shallow water underwater vehicles. So I want to discuss a couple of things about autonomy and provide a fundamental perspective of what we mean when we say autonomy. Now, obviously, when we deal with complex dynamic systems, whether they are ground robots, underwater robots, sea surface, or aerial systems, these are very high nonlinear coupled systems. And when we talk about autonomy and autonomous performance, each one of us means different things. And there is a mathematical formulation that could be behind studying all those systems. And so one approach could be to use the entropy for the reasons I'm going to elaborate later on. So long story short, today's talk is going to try to set a framework for studying and understanding autonomy. Now, I promise mathematics is going to be at a minimum, and then we will discuss the concepts. However, I want to jump into deep water and say that in terms of thermodynamics, statistical thermodynamics, entropy was defined by Boltzmann, and pretty much he defined entropy of a perfect gas which changes state isothermally at some specific temperature T in terms of the Gibbs energy and the constant, Boltzmann's constant. So pretty much entropy was defined in this way, and then years later, many years later, Shannon defined entropy for communications. So the entropy given a probability distribution P of x, then the entropy is defined Px log P of x, and then the transmission of information is defined in terms of entropies and conditional entropies. That's all we need to know. Entropy started as a measure of uncertainty of information. Now, what we are going to show is that it is also a dual measure, and it can be defined for control, for identification. Even Kalman filtering can be defined in terms of entropy. And so this allows us to discuss, to consider entropy for modeling and performance evaluation of systems. So now I'm going to try to put in context what is autonomy. Then we will go through a short history and a journey over the evolution of control system theory, and then discuss what has happened over the last 50 years when it comes to autonomy and autonomous systems. And of course, application of AI, because AI is not something that happened just a couple of years ago. It has been around for many, many years. Actually, for the older of us, I'm one of those, who were around at Boston, the first wave of AI funding and technology collapsed. That was technology, Route 128, America's technology highway. And the reason was not that the theory was not solid. We did not have any computational power, and we were not able to apply anything in real time. Keep this in mind. We were not able to apply anything in real time except something which was as complex or as simple as an inverted pendulum. So autonomy means different things for different people. When you look at the Google car or when you look at autonomous driving, you got from zero automation all the way to high automation, where the car is fully autonomous. Now, from this perspective, for better or worse, and I'm just stating the facts, I'm not taking a side, I got my own personal opinion, autonomy is a set of software capabilities. And so the dynamics of the car to some extent have been completely ignored, or something that has to do with uncertainty or anything that has to do to reacting to unforeseen situations. This has not been modeled in a mathematical way, has not been incorporated. You have a context well defined within which you define different levels of autonomy, okay? Now, although this is the case, and you define levels of autonomy in a car, when it comes to the US DoD and the 2010 roadmap, they did not want to discuss levels of autonomy. So it was just autonomy, and the curve from no automation all the way to full automation for unmanned systems, and it includes all different types of unmanned systems, followed this curve. And in terms of architectures, they were talking about 3 different levels of architectures, where at the highest level, you do consider the system, and then you have a trade-off analysis. Complexity versus fast prediction accuracy, and you really need to have a set of models which are either model-driven or data-based models, data all the time, and then you go to the higher levels where you have the human-machine interface, and then the system performs by itself. If I want to put this in system theoretic approach, then anything which is in yellow, it is underutilized. We do have capabilities here, but we need more. And the red one is what needs to be developed. One of the things that need to be developed is the situational awareness. And what do we mean by this? If you move forward to 2019, the new DoD map establishes autonomy in a completely different way. This just came out, and this is fiscal year 2017 all the way to 242. So here, for autonomy, you talk about trust, you talk about efficiency and effectiveness, and then artificial intelligence and machine learning is for the first time explicitly defined and incorporated in what autonomy means and what we need to do. Now, systems that our lab has developed, and we have a whole different set of autonomous capabilities. This started as a concept that the US Navy wants, the 3-in-1, where you have a sea surface vehicle where you can deploy some underwater robots, and then it is being used as a docking station for helicopters to land, recharge, and remove and continue their functionality. When it comes to ground and aerial vehicles funded by NSF and the Army, a whole series of ground robots, and then different types of aerial vehicles, lower altitude, which are the small quadrotors, high altitude, which are fixed-wing UAVs, and prototype systems which demonstrate different autonomous capabilities, landing platforms. Actually, the landing platform level, the surface, is a solar panel on which quadrotors can land, recharge. However, because of payload limitations, we ended up having a much larger ensemble UGV and landing platform, payload capability around 500 pounds, which is 230 kilograms. And then different types of UAVs of interest is this last UAV, which I will talk about when I come to Zagreb on Thursday. And this is a system which has on-board built-in capabilities to change lift-to-drag ratio, and therefore require less runway. So this is something which is based on circulation control, and by blowing air on the trailing edge of the wing, I increase lift. When I increase lift, then I require less runway. Experiments have shown that I can reduce the runway by 60%, or I can double effective payload. Where is the intelligence here? Where is the autonomy? When do I need to start blowing more air? Under what conditions? And when I need to stop blowing air and go to regular flight. The problem is very difficult. It's non-linear because then the aerodynamic capabilities change of the time and uncertainty is not structured. Therefore, I need autonomy. These you may consider toys. But when you go to helicopters, then the autonomy is in a different perspective. You need an integrity management. You need health integrity management, and part of it is prognosis. And you can play with our toys, but when you have such a helicopter, diagnosis, prognosis, and autonomy within the performance is awfully important. And if you want to go one step further, it is the F-35, which, even though there is a pilot on board, it has many autonomous capabilities. Now, we all talk about unmanned systems, but in reality, there is nothing unmanned about unmanned systems. There are 4 operators when it comes to UAVs. This is the US Air Force perspective. And Michael Toscano, AUVSI, is the one who said there is nothing unmanned about unmanned systems. The Army, on the other hand, wants to reverse what the Air Force says. The Army wants 4-to-1, one operator, 4 unmanned systems. And the main reason is when the soldier is somewhere in the field and 12 hours of 50 degrees Celsius or 45 degrees Celsius, they want to be able to control a whole bunch of small UAVs using a very, very small interface like our cell phone, which has to have primitive, very, very simple interface and coding and functionality, and then assets, unmanned such assets, take over and they control themselves. Either or, when it comes to any kind of unmanned systems, you have uncertainty at the individual sensor level, then you go to the component subsystem level, and then you go to the individual vehicle uncertainty to fleet uncertainty. As you go up the echelon, uncertainty increases. And we need to be able to accommodate this. So, the central objective, as DARPA puts it, is assured autonomy. Assured autonomy with performance guarantees. That requires delegation of authority from the human to the machine. And this is going to be in a gradual way, which, in our opinion, requires understanding of what the level of autonomy means. If I tell you level of autonomy 0.5 versus 0.7, how much more or less delegation goes from the human to the machine? And the end is what DARPA again says, high confidence systems. The attributes is reasoning, planning, replanning, situational awareness, fault tolerance, and health management. The tool could be intelligent control and applications of intelligent control. And then the challenge is the metrics for autonomy. And now, when it comes again to the tools and methodology, we have a plethora of tools. We are very fortunate that control system theory has evolved tremendously since the 50s. But the big question is, why now and not then? And this is where the computational complexity and the computational power comes to place. Why? Because back, if you want to talk about the history of controls and intelligent controls, foundations of classical control were established in the 50s. Then we had adaptive and learning control in the 60s. So deep learning, for the younger, is not the invention of the 21st century. Learning and learning algorithms were developed back in the 60s. We could not apply them, because I remember even as a student, I had a very small system, 3 or 4 or 5 states, and the Kalman filter took 6 or 7 hours to converge, leaving the program all night. I mean, we were using cards, okay? And then, I mean, right now, of course, everything is different. Then we go to self-organizing control in the 1970s, and Kang-San Fu at Purdue coined the term intelligent control. And then, in parallel to the 70s, the group at MIT, then at George Mason University, Alex Levis and his group decided to talk about decision makers. And they were the first who used information theory in the terms of Shannon, okay, to model decision makers. It was based on the so-called principle of bounded rationality, 1948 again, Herbert Simon, which says, I don't have perfect knowledge about something, I know a little bit, so my model is going to have bounded rationality. So rather than not making any decision, I'm going to make a decision based on what information I have, and then I will improve this decision based on learning. And then you go to the 80s, towards the last part of the 70s, again at Purdue, George Charidis and his group introduced what is called hierarchical intelligent control systems. And then we go to the 80s, James Albus at NIST, NBS, National Bureau of Standards at the time, he developed a 5-level layer manufacturing architecture which was for intelligent control systems and hierarchical systems. Antsaklis and Passino at Notre Dame came up with a similar multi-level architecture. Meistel at Drexel had nested hierarchical structures. Umitosgyner and Leventa Tsar had a formulation more mathematical based on some sort of formal design how to deal with such systems. And then it was the principle of increasing intelligence with decreasing precision, which was established by the Saridis group at RPI and continued being used by several groups. The Alex Levy's group, which was the first one that created the decision maker and the model of the decision maker, does not get enough credit. Years ago, he started with situation assessment and response selection. That was the only two. So pretty much you had a set of predetermined algorithms that, given an environment, the system chose one of those algorithms to start acting. And then based on the action, you had to select a response. And then you had the response selection. Deterministic systems, mostly used for the US Navy. The command up and down from the bridge all the way down until you fire a weapon and then you get back. Usually it took 20 minutes. And so you needed to automate this. Then the evolution of the digital computer started. So they had information fusion. You get information. So your situation assessment depends on the information that you have from sensors. Okay? Then it is the task processing. I get this information. I have to choose between different tasks. Which one am I going to choose and how am I going to perform it? Which has to do with the command interpretation. And then you have the response selection. For those of us who are in system theory, this has to do with command control and communication, then command control, communication, and intelligence. There is a background in all of this. All of this was evaluated in terms of information theory, transmission of information, throughput, blockage, noise, and coordination. All this is mathematically established and works pretty well. If you want to move very fast forward, you end up in Portugal with Fekri and Mike Lathans after he left MIT, and here pretty much you have something which we call now switching adaptive control. For systems, airplanes, that was for the Airbus and for the 767 and the F-16, you have a whole bunch of Kalman filters and a whole bunch of models. So given the situation of the system and the operational conditions, the environment, you choose a specific Kalman filter and a bunch of models which have been proven to be locally unstable, and then you evaluate the performance of the system. What is the critical issue here? The critical issue is, of course, how fast you switch, how you update your model, obviously, and how do you know where to update your model. So this is the back and forth. So in general, when we talk about autonomy, we actually talk about systems which can be modeled based on different hierarchies. And hierarchies have been used not only in engineering systems, but also financial organizations, societal organizations. The number of levels is not important. What is important is what happens, what is the functionality within each level. This is the Saridis approach, this is the Anchaklis approach. You see two different architectures which are functional architectures. They are not actual mathematical architectures. It's the functionality that allows you to determine and evaluate autonomy. And there is something else. At the lowest level, you got a time-based approach. It is our famous integrodifferential equation that governs any robot vehicle, any airplane, anything. And then at the highest level, as you go up, is event-based. Event-based. Quantitative at the lowest level, qualitative at the highest level, and then how you go top-down, it's a matter of how abstract models can be translated into the integrodifferential equations, your state space x dot equals ax plus bu, that you have to describe your actual system, which consider here that the lowest level is your underwater robot, your UAV, your ground robot, whatever. This one is advantageous because it is modular, it is both spatiotemporal, it does have explicit human interaction. One of the criticisms that our group has is, how do you model human interaction? What does happen in the human-machine interface, and how will you be able to evaluate that? So, if you want a very general mathematical framework in very abstract terms, you got a system, consider it that it is an intelligent machine, one of our robotic vehicles. Somehow you have a command. That could be either a speech command or could be a typed in command. You need to classify for the machine to understand this command. And then at the higher level, which is the organization, pretty much you have a bunch of scripts or a bunch of scenarios. You need to evaluate based on accumulated knowledge and information which one is the best scenario. Obviously, you need adaptation and learning, which comes later into the loop. Once you choose based on accumulated knowledge, intelligence, that happens by itself, right? That's why I talk about autonomy. Then you decide about a specific scenario. The coordination level then does one thing, finds the best way to execute this specific scenario. You have ranked the different scenarios. So if this scenario is not executed, you go to the next possible, probable, whatever. You can follow fuzzy set, probability theory, formal specifications, hybrid systems, whatever you want. And then you actually execute. The good thing about it is that information goes from the lower level to the higher level, but you do not jump levels, layers. It is from the immediate lower level to the immediate higher level. Those are the famous, today we call it deep learning, right? These are the famous stochastic approximation algorithms, probability algorithms that introduced learning. And it took forever for these to converge. And if you don't know the performance of the system, you observe the performance, which is the observed performance, and then you calculate the performance based on accumulated information. There are a couple of theorems here, Dvoretzky's theorems for convergence, for those B and gamma coefficients for this to converge. Since you can evaluate probability, you evaluate entropy. Minimization of entropy is minimization of uncertainty, therefore increasing intelligence and autonomy. And then if you want, for robotic systems, any robot system, you have a whole bunch of coordinators. You have your sensor coordinator, your motion coordinator, your controller, your vision system, which is usually different than anything else, other sensors, because it's a whole complicated area by itself, and you can evaluate again everything like this with entropy. So that happened in the 80s. You go back about 5 years ago, Valavanis at Georgia Tech talks about a DCBR, dynamic case-based reasoning. So here is a database which is both model-based and data-driven, and what you do, you accumulate all the information about how you execute, formulate and execute a scenario. And also you have similarity indices between 0 and 1 between different approaches, how you execute, how you formulate and how you execute. So if the similarity index between two different scenarios is 1, they're identical, almost identical in terms of execution. If there is 0, one does not relate to the other. So you build, this is the heart and soul of your system when you want to evaluate autonomy. So you build this library, and eventually, as the system continues to operate, the accrued knowledge contributes to how the system can make decisions by itself without human intervention or with minimum human intervention. And Q-learning, incremental learning, which we could not apply in the 80s, is directly applicable here. Another instantiation which has to do with the system that I showed you at the beginning with UAVs and UGVs is this architecture, which has been developed by Notre Dame and us, which has different types of unmanned vehicles. It is a hybrid architecture, and we follow a formal design, formal specifications, guaranteed performance to model this system in uncertain environments. So this gives you an idea of the complexity of the systems, the complexity of the approach, and so now how do we implement it? First of all, why entropy? I told you that the entropy is a measure of uncertainty. However, entropy has some fantastic properties compared to other measures to evaluate autonomy. The papers by Lloyd and his group are pioneer in this area. Why? Because they talk about different measures and similarities and differences and difficulty in implementing them. So why entropy? Entropy has a dual meaning. At the highest level is a measure of uncertainty defined by Shannon. At the lowest level, however, it is a control performance index, as I will show you in a while. Also, it is invariant to transformations. Entropy is entropy. It does not change if I want to transform my system. And therefore, it is a unique measure. With entropy, I can deviate from the optimal solution. Optimal, suboptimal, stochastic, or deterministic. There is something that is important for control people. Robustness, robust intelligence, robust autonomy. The difference in entropy allows you to see, to measure how robust is your system. And so how we are implementing this? We have to understand how to model confidence, risk, RUL, remaining useful life if a problem occurs in a system, and then resiliency. Now, resiliency and robustness are two different things. We tend to mix them. Robustness requires structured uncertainty, and we know how to design a controller or a bunch of controllers within an interval, upper and lower bound of uncertainty. We know the uncertainty. Or we design a whole bunch of controllers depending on how we quantize that uncertainty. Resilience is more general. I don't really know the uncertainty. The bounds can be different, are not very well designed, and therefore the measure of resiliency here, what happens is allows me to go beyond robustness and understand whether my system performs within acceptable limits. And so now, how do I put all this in a quantitative framework? Please understand, quantitative framework, not quality of service, not quality-based evaluation of system performance. So let's go back. This is the Boltzmann entropy in statistical thermodynamics. How am I going to use entropy for control? It turns out that it is not that complicated, but the theory, the idea was brilliant when it was captured back in the 80s. When you deal with dynamic theory of thermodynamics, on aggregate, you can define, okay, the performance over time of the state in terms of a Lagrangian, okay? And then, if you define the Lagrangian formulation, those two are equivalent, and this equation is defined where it is the constant temperature and I is your Lagrangian. So you connect entropy with a Lagrangian formulation. Once you define the Lagrangian, then the door is open for control theory. Let's consider now a very fundamental control problem. Let's consider the deterministic optimal control problem, where a class of systems, x dot, is given by a function of the state, input, and time, okay, with some initial condition. The performance index is given in terms of the Lagrangian. And then what happens is that if you choose the optimal control that minimizes the cost, you get this solution where U star is the optimal control. So what Saridis did, put that formulation in terms of entropy, and the idea was to minimize the differential entropy, where P of U is the probability of admissible control sequences. You don't have just one input, you have a set of admissible inputs. So by minimizing the worst entropy, you minimize the uncertainty. This is entropy as control at the lowest possible level. To make it a little bit more general, the Hamilton-Jacobi-Bellman equation is in terms of entropy. And you minimize the performance index, which means, or you maximize, it means that you have an optimal solution. The adaptive control problem is similar to that. Paul Kalata-Drexel wrote 4 papers in which he proved that entropy can be used to identify parameters of system, and he had the different formulation of Kalman filter based on entropy. So when you minimize entropy, you minimize uncertainty. When you minimize uncertainty, you improve machine intelligence. When you improve machine intelligence, you improve autonomy, because then the system operates by itself. What is the interval? It is the interval between maximum and minimum entropy. So you have the worst and the best case scenario. So this interval, in terms of probabilistic analysis, it gives you the robust intelligence, or it gives you the different levels of autonomy. The more you quantify that interval, the more levels you have. The more refined it is, the more gradual the performance between one and the other. And I left also, what is the human interaction? How do you interact? How is the human part of the loop? Before I give you a couple of very simple relations, I will go back and tell you what the Air Force and the Army wants. The Air Force says human in the loop. It doesn't matter how smart the airplane is. And right now, by the way, there are completely unmanned F-16s. Completely unmanned F-16s, which are the wingmen of a manned F-16. But they are, at this point, they are mostly in leader-follower form, master-slave, so the unmanned F-16 duplicates the moves of the manned F-16. So what happens here? The Air Force says human in the loop. The human is always part of the system, and the human approves every decision. The Army says, no, I want human on the loop. On means if and only if absolutely necessary, then I will be part of the loop. So in this case, if you evaluate entropy, probability density function says the sum of all the individual probabilities is 1. Maximum entropy in this case is the uniform distribution, 1 over n. And if you look at the second equation, all the C's are weights that go with the individual probabilities. So this second equation is the machine-human interaction. The human can bias the machine to follow certain plans better than others. So by choosing these C's, and by entering these C's into the system, you reevaluate again all the performance indices and the entropies, but this one shows how the human interacts mathematically with the machine. What changes is the H-max minus H-min, because if you incorporate the knowledge of the human into the machine, that interval decreases. So under this formulation, you can pretty much model any complicated system. And this complicated system, in the most general form, is given by a set of, this is the dynamic system. If you have any number of levels, you model each particular level on an individual basis. So you got the inputs, you have the noise, you have the human input, which is directly coming into the system and affects how the scenarios are formulated, okay? And you go all the way up and down the echelon, and this one, you see what goes through, what is being blocked, how internal decision making is being considered, and this could be either deterministic or stochastic, and then what is blocked, what does not go through. So in terms of application, we have gone through a whole series that includes validation and verification. Validation and verification has become extremely important. Companies like Lockheed, which have suffered tremendous losses, losing satellites. They were not even able to launch them. The latest one about 9-10 years ago in Florida, about $1 billion worth of research and development, could not even launch it. And the main problem was that if you have, these are complicated systems, and validation and verification should happen at the component level, subsystem level, and also at the overall system level if you want autonomy and autonomous functionality under the proper context. So you have offline validation and runtime validation. Offline validation obviously is what most of us are doing, in the sense before I test the system, I run some troubleshooting and everything seems to be fine, and then I try to implement it in real time. However, when I implement in real time in parallel, I need to have the runtime validation, which allows me to update the system. So these are the things that need to be considered when you actually consider autonomy and autonomous functionality. And in terms of real systems, what we have done is when you have the so-called reconfigurable UAVs. UAVs, thus far, fixed structure, fixed wing, and everything. The next generation of UAVs, fixed wing UAVs, are going to be reconfigurable morphing UAVs. Morphism has to do with change. The fuselage is not going to change, but the wing configuration will change, following bio-inspired approaches, for example. And so the wing can change in plane, so wings can be extended, and there is a critical point about 75% when you extend the wing, then the aerodynamic capabilities of the system change, or could be in 3D morphism. And so that creates a whole different set of flying capabilities for the vehicle. Something else that NASA Dryden in California is very much interested in, the so-called segmented control surfaces. So you have the wings, okay, of any system, a plane. Something goes wrong in the wing, and you cannot control the wing. Well, that's not a good thing. So how about if I divide the wing into different segmented surfaces, and if something is wrong in one surface, I can still control the rest of the wing. These are things that are part of the autonomy framework. Now, these are very highly mathematical problems, as I told you before, and there needs to be a common measure to evaluate functionality of these systems. The good thing about the approach that I hinted, not trying to push it, I hinted this approach and we are using it, is because of its additive properties. So the uncertainty here could be uncertainty of one part, of one component, or the overall system. Most important of all, for the system under considerations that we all work with, we do not know the nominal plant. These are systems where one plant is not enough. So we have different models. So I have a family of models for which I need to design my controller. The traditional approach thus far, the engineering way, was divide and conquer. Gain scheduling, all right, where I have a whole bunch of controllers and a whole bunch of models, and I switch from one to the other. Switching adaptive control is the other approach. Fuzzy logic and neural networks is the third one, but there is a problem. Unless I have tons of data, then my system is not going to perform in a stable way. So the idea is, how do you use this framework if you have a whole bunch of admissible models? How do you build one controller, and how autonomous is this system? And the entropy concept is something that allows you to measure the autonomy and measure the intelligence of the system. So the notion 0.5 versus 0.7 gives you a quantification of levels, and it allows you to understand how accurately the system functions at the lowest possible level, it's your controller, and how smart the system is in formulating the scenarios that are going to execute an assigned mission. And pretty much, if we want to study autonomy, just pick a system, follow any approach, and understand the differences between autonomous functionality. that's what I wanted to discuss with you today, and thank you very much, and I'm open to questions.